So far we have seen the simplex method for solving linear programs, and we have seen two ways of implementing the simplex method. So one was using the equations and the other one was using the simplex tables. So the simplex table made our life slightly easier for doing the substitution process. Now when it comes to implementing the simplex method on a computer, people often choose a third way of doing things, which is called revised simplex. So that basically does the exact same thing that we have seen so far, but they do all of those things on matrices. So why do people do that? Because there are efficient algorithms for doing matrix multiplication and computing inverses of matrices. So that makes the overall process far more efficient than the table version. So let's see what this revised simplex method is. Okay, so let's say we have this linear program which is Cx, Ax equal to b and x is greater equal to 0. So let's represent A as set of columns like this one. So A1 is our first column, A2 is our second column, and so on and so forth. An is our nth column, last column. So each column is for each variable, right? So A1 is the coefficients of the first variable, A2 is the coefficients of the second variable, and so on and so forth. Now what we are going to do is we are going to divide this three matrices C, A and X into two parts. So one part is for basic variables, the other part is for non-basic variables. So something like this. So columns of A will be B and N. B is the set of columns which are for basic variables and N is for non-basic columns, right? So the coefficients of the objective, that is C, is also divided into two parts, so which is CB and CN. Same for X. X is divided into two parts, basic variables XB and non-basic variables XN. So if we rewrite this equation Ax equal to b in terms of this decomposition, then it will look something like this. So A is Bn and our X is XB and Xn. So if you do the matrix multiplication, it will be B times XB and N times Xn, and that is equal to our right hand side B. Now if you want to find the value of xb, then what we can do is we can just move these n xn terms on the right hand side of this equation and then multiply everything by b inverse on the left hand side. So it will give us something like this. It will be b inverse b minus b inverse n times xn. And we often use a shorthand notation for this term, which is b inverse b, as xb. Why? Because we know that our non-basic variables basically take values of 0. So this entire term will vanish and xb will take this value x hat b, which is b inverse b. Okay, so let's do the same thing with our objective also. So it is C transpose x. So let's decompose it. It will be CB Cn times XB Xn. It will look something like this. And now what am I going to do is I'm going to substitute this xb, which is b inverse b minus b inverse n xn, into this equation. So that will give me something like this. That is C transpose b inverse b plus Cn minus Cb b inverse n times xn. So that's a kind of complicated formula, but it's kind of very useful. Again, so xn is going to take the value 0 in our solution. So the final objective will be CB b inverse b, depending on which variables we choose as our basic variables. And this is the coefficient of non-basic variables, xn. So if you remember correctly, then in our simplex tables, we use the coefficients of non-basic variables as our reduced cost, right? So again, here also, this is our reduced cost. So note down this formula. This is kind of important to remember. We will use this formula to compute reduced cost directly. So yeah, it's kind of helpful if you note it down. Okay, now we know the basic components, we know the reduced cost, so we can actually even pick our entering variable. But how do we pick our exiting variable, right? So given our basics and non-basic variables, we know how to pick one of the non-basic variable as our entering variable. We basically compute this reduced cost, and whichever variable has a negative reduced cost is kind of eligible as our entering variable. So let's see how do we compute the exiting variable. So we can pick first an entering variable with a negative reduced cost. Let's call it xe. Okay, I mean e is also used for exiting and entering, but it's kind of confusing. So let's remember that here e is for entering variable, not the exiting variable. Okay, so xe basically is our non-basic variable. So it has some reduced cost, and if xe goes from 0 to 1, then the objective is going to change by its reduced cost. So let's again recall our formula for xb, which is b inverse b minus b inverse n times xn. Right? So all other non-basic variables are going to take value 0, but we want to increase our entering variable. So which columns of n are kind of useful is the column for our entering variable, right? So everything else is 0. So this second term will be basically b inverse the entering variable column times the entering variable. Okay, and let's also like denote this term b inverse ae with a simple notation. Let's call it de, right? So minus b inverse ae is de. And so what does this mean is that we can actually rewrite this entire equation like b inverse b, that is x hat b, plus coefficient of xe, which is de times xe, right? So this entire term is de times xe. So it will look something like this. So for a particular basic variable xi, ith basic variable, it will be again x hat b, which is x hat I. We are now strictly looking at single basic variable, so it will be x hat I, and di times xe. So now again, so de times xe. Now again we are looking at the ith variable, so we only care about die times xe, right? So that's the ith component of de. So that's our basic variable. And remember how we picked our exit variable? So that's basically the one which restricts our entering variable the most, right? So how is this basic variable going to restrict our entering variable? So it takes the value which is negative, then it is kind of restricting, right? So we can increase our value of xe, and if this die is negative, then it will eventually reach to this xi hat value and make this basic variable 0, right? So basic variable xi will reach the value 0. So first condition is that die has to be negative. So if die is positive, then it is not really restricting our entering variable to increase, because if we increase it, then xi will remain, this value is positive or non-negative, and di is also non-negative, so everything is non-negative, so it's not going to really restrict our entering variable. So di has to be negative, and xi hat is when it equals to minus die times xe, then this xi will become 0. After that it will start going negative, and that's kind of going into infeasible space. So our xe can take the largest value, that is xi hat divided by minus die, right? So this is exactly the same thing that we have been computing as our ratios. So this is how we will compute our ratio in our revised simplex method. So we compute this xi hat, which is b inverse b, and then we compute this de, which is b inverse times our column for our entering variable and negative of b inverse times ae, and then we divide this x hat value with this de part, right? So this gives us a set of ratios, and then we pick the ratio that is smallest, right? That gives us our exiting variable. Okay, so let's see how all these things apply in an example. So let's pick again the same example that we have been solving so far. So it's minus 3x minus 2y, x minus y minus s1 equal to minus 2, minus x minus y minus s2 is minus 6, minus 2x minus y minus s3 minus is equal to minus 10, and everything is greater or equal to 0. So we want to decompose our a, c and x with basic and non-basic variable, and if you remember correctly, in our first iteration we chose S1, S2 and S3 as our basic variables, and X and Y were our non-basic variables. So let's first of all rewrite this A in terms of this matrix format. Right, so it's basically the coefficients of X, Y, then S1, S2 and S3. So if we list them down, then it will look something like this. So these are the coefficient of X, which is 1, -1 and -2. Then coefficients of Y, which is all -1. Coefficient of S1, here it is -1 and in the other two it is 0. So it is something like that, and so on and so forth for S2 and S3. So our basic variables are S1, S2, S3 and our non-basic variables are X and Y. So based on this choice of basic and non-basic variables, we can also decompose our objective coefficient. So for objective coefficient, the coefficient of X is -3, Y is -2 and S1, S2, S3 are 0. So our X coefficient for basic variables, which is CB, will be all zeros, which is coefficient of S1, S2 and S3, and non-basic variables will be -3 and -2. Now again, like we can use this decomposition to compute our B matrix, which will be the columns corresponding to our basic variables, which is S1, S2, S3. So it will be this part of this matrix, right? So the last three columns, and the non-basic variable, the non-basic part, which is N, which will be our first two columns of A. So it will look something like this. So using all these things, we can first of all compute B inverse, because we are going to use B inverse so many times. So let's compute B inverse. In this case, B inverse apparently is same as B because the way it is structured. And using that, we can actually compute the first thing, which is our reduced cost for our Xn. So if you remember the formula, it is Cn minus Cb, B inverse N. So let's compute that. So it will look something like this. So we have our Cn, we have our Cb, we have our B inverse, and we have our N. So we have everything. So we just do this matrix multiplication and this subtraction, and then we get our reduced cost, which is -3 and -2. So -3 is the reduced cost for our first non-basic variable, that is X, and -2 is the reduced cost for Y. So I don't want you to do these computations by hand, because this kind of messy, and it can get really annoying. So let's just watch the slides for now, and if you want to actually do all this computation, I would suggest doing things on a computer, right? So either use an Excel or use some programming language to do all this computation, but don't do it by hand. So it will then get annoying. Okay, so now it's time to pick our entering variable. We'll take the shorter path to our optimality, because this is annoying for me to present as well. So we'll pick X as our entering variable with -3 as our reduced cost. Okay, so next part is to pick our exiting variable. So remember the process. The process is first compute the value of X hat B, right? So XB will be B inverse B, which is 2, 6, 10. Then we compute the value of DE, which is B inverse our column for our entering variable, which is AE. That will give us 1, -1 and -2. And now we compute the ratios. So for the first one, the DE is positive, so it is not restricting our entering variable. For the other one, it is 6, and the last one, it is 5, 10 by 2, 5. Right? So we divide it with -DE. So the smallest ratio is 5. That means our exiting variable is the third one, which is S3. Now, when we exit this variable, we don't really need to do a lot of algebraic computations. All we need to do is replace S3 with X in our matrices. So for example, our XB will look something like this. So earlier it was S1, S2, S3. Now it is S1, S2 and X. And here it was X and Y. Now it becomes S3 and Y. Same thing with CB and B and N also. So CB will become, earlier it was 0, 0, 0. And now it becomes 0, 0, -3. So -3 is the coefficient of X in our original objective. And same for Cn. So it was -3, -2 earlier, and now it becomes 0, 2. If you just want to remember, this is our A matrix. Using that, we can compute our B. So B will be the columns of S1, S2 and X. So S1 is this is S2 and X is this. So this gives us B as the first column, this third column, fourth column and the first column, and the N is the remaining two columns, right? So again we follow the same process. We compute B inverse, which will be like this. Then we compute our reduced cost using our formula. So again, very important to remember this formula, which is Cn minus Cb B inverse N. This gives us this as our reduced cost, 1.5 and minus 0.5. So the negative one is this one, minus 0.5, which corresponds to variable y, which is the second one. So our entering variable is y. And now we need to pick our exiting variable. So again the same process. First we compute B inverse times B. So small b was minus 2, minus 6 and minus 10. So multiply that with B inverse. And our AE, the entering variable column, is for the y, that is all minus ones. Let's compute it. XB is B inverse B, which is 715. And DE will become this one, minus 1.5, minus 0.5 and minus 0.5. So all three of these columns are restricting. So let's see which one restricts it the most by computing the ratios. So ratios looks like this: 4.67, 2 and 10. The smallest one is 2, which corresponds to S2, and so S2 will be our exiting variable. So replace y by S2 everywhere in our matrices. So the first one looks like S1 y x, second one looks like S3 and S2, the non-basic variables. Now same thing with objective coefficients. That will be 0, minus 2 and minus 3, that is coefficient of S1, y and x in our objective, and Cn will be 0, 0. Our A was as before, it doesn't change, and using that we can compute B and N. So B will be the columns of S1, y and x. So columns of S1 is this, y is this and x is this, right? We use that and compute that thing, and this should give us our optimal answer. So let's compute it. Let's see if our reduced costs are all positive. So let's first compute the B inverse. It will look something like this. And now if we compute our reduced cost, then it will be 1 and 1, which is both of them are positive. So we have reached our optimal answer. So this dictionary is optimal, but we are still yet to compute our optimal variable values and our optimal objective value. So let's compute them to finish this method. So A was like this. Our SB was S1, Y and X, and XN was S3 and S2. Using that we can compute our CB, that was 0, minus 2, minus 3, and Cn was 0, 0. This was again like same as before. We have already computed all those things. So the formula for XB is simply B inverse B. So we had B inverse, we had computed it, and we multiply it with minus 2, minus 6 and minus 10, which is right inside of our original problem, and it will look something like this, which is 4, 2 and 4. So if you remember correctly, it actually corresponds to our actual solution, where X was taking the value 4, Y was taking the value 2, and S1 was taking the value 4. Now using this, we can also compute our final objective. If you remember the formula correctly, then it will be something like this. It is CB times XB, which is B inverse B, and the reduced cost of Xn times Xn. Okay, so this Xn is already 0, so we don't really need to worry about the second term at all. And the first term, we have already computed B inverse B, so we just simply multiply this with CB. That should give us 2 times 2, that is minus 2 times 2, that is minus 4, and minus 3 times 4, that is minus 12. So total is minus 16, which is our final objective value. So this is our overall revised simplex method.